So this is an opportunity for interested proposers to come up and share information of whatever type they want about the information related to proposals that they want to talk about. So we've encouraged people to share information about projects that they're interested in proposing and they want to lead. Maybe they're looking for a partner to come in. Maybe they have a capability that they'd like to contribute to a team that might be led by somebody else. Kind of sky's the limit in terms of what each of the proposers wants to share. So we received a number of slides from interested parties that we're going to bring up here. Bringing up for me on the monitor. So we'll introduce folks one at a time. We allotted quite a bit of time for this to make sure that we would have more time than we needed. We're not going to fill the full amount of time. We're going to let people talk for a little bit longer. In the past, we've said 1 to 2 minutes to be able to fit everybody into 2 hours. In this case, we'll give you maybe 4 minutes or so per person per topic. There are some people who have more than one slide because they're interested in talking about more than one topic. I'm going to turn and look at the slide behind me. All right, so we're going to go through each of the topics. So we're going to start with 8.1. We're going to progress through 8.5. So we'll start within each topic. We'll start with the in-person presenters. Single slide. I've already described what that's for. And here we go. And then so please, if you're online, you can reach out through the Whova app, or if you're in the room, you can reach out through the Whova app that we're using for streaming the event directly. Presenters should hopefully all be sharing their contact information as well, so that you can reach out to them after the event more easily. So why don't we go, maybe I'll just ask you to move to the next slide. So in topic 8.1, which is of course our additively manufactured 3D devices with increased complexity, our first presenter will be, all right, SWR Technologies. Shenming? Okay, there you are. Excellent. Absolutely.
So good morning. My name is Shenming Shen. So from SWR Technology. Our main topic of interest is 8.1, although I believe it's also very, very applicable to the rest of the topics, because we are not a manufacturing process developer, but instead we are the user and application developer for this technology. So I think this is something we'd like to bring to the table here. The main use case here we're talking about is transparent AR, is augmented reality. So as you can imagine, the HUD display, all this kind of thing, that could be utilized and to benefit from this technology. We have a FHE highly integrated. And so for us, we are specialized in doing wireless power electronics design. And so we have developed a through barrier wireless power and data system, and that is capable of delivering more than 1,000 watt at more than 95% efficiency in terms of power. In terms of data, we can do more than gigabit per second. That's the kind, and have a latency of less than 3 milliseconds. That's the technology we have. In addition to that, we also have the experience of developing a transparent heater, and that is a technology also leveraging some hybrid electronics to deliver the transparent heater. So we had experience of being a successful DoD SIPR Phase 2 awardee. And so I look forward to talking to anyone who does FHE manufacturing, because that clearly your manufacturing process capability is critical. And if you are doing any transparent display capability for doing so, I'd love to talk to you. And anyone else that could benefit from our electronic design expertise, I'll be glad to talk to you after the meeting in person here. Or if you want to reach out to me, that's the website as my contact and my information. And want to thank you very much for your time, and for Scott for generosity for the time, because I do think I need to get off in 60 seconds. I believe I used 120. Thank you very much.
All right. So I believe our next, okay, we're moving on to topic 8.2, and I believe our first presenter in that topic will be Dr. Pradeep Lal from Auburn University. Is that correct? Excellent. So Pradeep, you're up. Thank you.
Thank you, Scott. So in topic 8.2, we are proposing on the area of thermally enhanced, sustained high temperature, high power additive packaging. The use case that we have picked is on automotive applications. The primary reason being that this is a high volume consumer product that shares a lot of space with the military and defense applications. The intent is to actually create these solutions for the XEV, which broadly might mean battery electric, plug-in hybrid electric, or any other version of an EV platform that requires high power, high temperature under hood operation at 250 degrees centigrade or higher. What we hope to be able to do is leverage some of our prior experience in development of conventional electronic packaging architectures for the automotive underhood. So semiconductor packaging solutions that have been developed, for example, in the Cave 3 Center for operation at 250 degrees centigrade of sustained high temperature operation for an extended period of time using conventional methods. Some of that expertise is going to be leveraged for the additive solutions. The current version of the automotive electronics platform requires a lot more electronics, mainly for onboard diagnostics, for ADAS type of applications, and a solution in this particular space would actually allow for a much higher degree of integration of electronics into the underlying structural elements on the automotive platform. Some of the prior work on characterization, modeling, and life prediction on the automotive platform would be leveraged from that use case to generally develop requirements for additive semiconductor packaging, mainly for operation in harsh environments, which could then be leveraged for military and defense applications. So we have a couple of the team members identify what we are looking for are perhaps material suppliers in companies specifically that have materials compatible with sustained high temperature operation that they would like to include. We do have a base set, full disclosure from that standpoint, and any interconnect solutions, solder ECA solutions that are intended for sustained high temperature operation. We would like to have a conversation as a part of the team. And automotive companies that are interested in risk mitigation in the use of additive packaging on their next gen platforms. Thank you.
All right, so our next presenter is going to be our first virtual presenter of the day, Kurt Christensen from Optimec. So for the in the room audience, for our virtual presenters in this portion of the event, we're just going to hear them. We're not going to see them on the screen, but we'll see their slides here. So Kurt, can you hear us and can we hear you?
So we're looking at high performance FHE Interconnect. We've been working on a NextFlex 6.7 project with Lockheed Martin and Binghamton University, making a 6 gigahertz phased array radar system. And so this is phased array radar requires on the order of 100 transmit receive channels. So reducing the size of these is important. Also, I don't have a picture of it here, but they've actually folded the Rotman lens, very impressive. Didn't have room for the picture. What we're looking at for the next project is extending this to 28 gigahertz. As it goes higher, the parts get smaller, so you can put them in smaller areas. Think in terms, for instance, of a drone, lower cost drone that would crash into or explode near a incoming low cost drone. You know, we can't be spending $1 million to shoot down a $20,000 drone. So in general, reducing the size, improving SWaP-C. So this has 5G and military applications. Right now, we're actually testing our technology at 120 gigahertz with a couple of advanced customers. Certainly the 28 gigahertz, it works. It'll be interesting to see how print interconnects work up at those higher numbers. We'll be emphasizing, obviously, design rules. For instance, as I've been printing these things, I found out, doctor, it hurts when I do this. So we're going to, develop design rules. Also, materials, they're not ideal in all cases. Thermal performance, right now, if you look at this amplifier, it's not heat sunk well. And so can we, how do we connect if we put that down in a pocket and put it on a thick ground plane on the back? And then RF performance, is just the right shape for the conductor? Well, it's better than straight, but we don't know the ideal shape. So those are, kind of areas that we're looking at continuing in. And for partnering with others, if anybody needs to, do this kind of connection, we're getting pretty good at them. Or for instance, silver epoxy dots, if you're doing a flip chip, we make those small or underfill it. Microfluidics, that you need to have a glue bead put in a very specific spot. Those, if you're interested in any of those kind of things, give us a call. Thank you.
All right, thank you, Kurt. All right, so we're next going to move on to topic 8.3, the harsh environment hybrid electronic components with proven reliability. And I believe our first speaker is an in-person speaker. We'll hear from Pradeep Lal again. Okay, Pradeep's at the back of the room. I'm sorry. So we're going to start with the virtual in this case. All right, I'm sorry. Change of order. We're going to start with the virtual presenter, Dr. Masood Atashbar from Western Michigan University. Masood, can we hear you?
Do you hear me?
Yes, we can hear you. Excellent. The floor is yours.
All right, thank you. Just a note that I didn't see Kristen slides. All right, but I see mine. Thank you. So Western Michigan University is one of the founding members of the NextFlex and is a pioneer in flexible and printed electronics since 2007. In project called 8, we seek partners to collaboratively submit a strong proposal for topics 8.3 and 8.4. In 8.3, we focus on printed coating and improve electromagnetic interference shielding. WMU, along with SafeSense Technology, has a strong prior experience in developing highly conductive standalone graphene film with a conductivity of more than 1.3 million Siemens per meter and EMI shielding efficiency greater than 100 dB. We plan to develop graphene-based ink formulation for screen printing and spray coating that can be deposited at ambient conditions onto various substrates. We target an EMI shielding efficiency of greater than 60 dB. We are looking for a partner who can provide the NextFlex intended use cases for this project and help with performing environmental testing. In topic 8.4, we focus on high volume manufacturing of multi-layer passive components. WMU recently acquired a roll-to-roll screen printing from Systech, which is being installed on campus. The printer is capable of high volume commercial manufacturing of components with advanced automatic registration system and in situ thermal and UV-based annealing capabilities. We are looking for partners who has expertise in FHE-based ink system for screen printing and prior experience with establishing standard process parameters for printed resistors, capacitors, and inductors. In terms of WMU capabilities, there are 3 centers at Western Michigan University that are focusing on flexible hybrid electronics, which they are CAPE, CAS, and STL Lab, which have been in collaborating for the past 15 years. We have extensive research expertise, including ink formulation, characterizing of ink and substrates, printing, and post-printing characterizations. WMU has various printers, including gravure, flexography, screen inkjet, and aerosol jet printers. We have a goniometer for wet studies, rheometer for rheological characterization, image experts, SEM, AFM interferometer for print quality characterizations, and Markton, as well as Instron tensile tester and other customized equipments for performing mechanical characterization. In addition, WMU has various equipments for ink making, processing, and FHE-related functionality characterizations. These include ink mixers, ultrasonicators, XRD, network analyzers, plasma systems, environmental chamber, photonic sintering systems, and laser system. Thank you.
All right, thank you, Masood. All right, so now we're going in the other order. So I think now we'll move to Professor Pradeep Lal. All right, there, Pradeep.
Thank you, Scott. So in this particular topic, what we are proposing is a solution for extreme high temperature, wide temperature, extremes, high G reliability of FHE. And the intent is to really understand the failure modes, effects, and criticality analysis of some of the failure mechanisms and failure modes that may exist in additive semiconductor packaging. To be able to understand the accelerated tests that are required, the accelerated test levels that are required, to be able to assure operation for a certain duration of time in the end use scenario. So there is a vast body of literature that we hope to be able to leverage on our prior work in failure modes and mechanisms, specifically in harsh environments for other application use cases, where we have looked at accelerated tests, development of accelerated test levels. We have also been a project lead on a project called Topic 2.5 much earlier on, where we focused on development of accelerated tests and accelerated test levels specifically for flexible hybrid electronics. And we hope to be also able to leverage PC 7.6, which is in-mold electronics specifically for automotive applications, which would yield technology product demonstrators that could be used for this particular proposed program. So we are hoping to be able to partner with our companies that may be interested, for example, in migrating an existing design to an FHE space. We have one such use case currently that is going to be a part of the proposal. Or we're also looking for partners that may be accelerated test companies that may have innovative new testing methods that they would like to have included, for example, specific to FHE that would circumvent some of the traditional testing that is done for conventional electronics to be able to ascertain or compress the use case stresses on an accelerated test platform basis. Any OEMs or first or second tier companies that may be interested, for example, in risk mitigation would also be a wonderful partner to have as a part of the team. Thank you, Scott.
All right, next we'll move on to the topic 8.4, the heart. I'm sorry, I have a question, perhaps. Yes, Eric? Sorry, Mike. I'll repeat, go ahead.
ARL has a 100 kg drop tower, and we're happy to do some testing for you, so just let me know.
That's fantastic. So I'll just repeat back the first part. So the Army Research Lab has a 100 kg drop tower that they may be able to provide for interested parties or provide access to.
Eric, we would very much welcome that. We have one as well, and we would love to do some validation testing as a part of the round robin and see if the test methods perhaps correlate on multiple sites. Thank you.
All right. So actually, Pradeep, why don't you come back up? So in topic 8.4, the harsh environment, hybrid electronic components, is that where we are? Yes. Pradeep, you are the first speaker in that topic as well. I certainly hope. Yes. Okay. Good.
Thank you, Scott. So this topic is markedly different as well. The focus is largely on manufacturing design rules. So there's been a lot of work that we have done on prior programs, PC64, PC65, for example. 64 dealt with assembly of components onto additively printed circuits. OPC1, where we actually develop processes for additively printed multi-layer circuits with Z-axis interconnects, and 65 that focus on closed-loop control. So the intent in this particular program is really to develop manufacturing design rules and process reliability performance interactions that could then perhaps be standardized. And the standardization would allow for manufacturing design rules that could then be implemented as a part of a high volume process uptake in multi-material assemblies on a number of different platforms. The intent is to really quantify, for example, sigma levels, for example, the defect rates, the yields that could be expected for certain process sets as these processes are being migrated into high volume solutions on major production products. So we have certain materials that actually we have studied, and there is a team in place. But what we want to be able to do is we want to be able to be a little bit more inclusive, because there are new materials coming up that are more recent than some others, and we would welcome any material companies, for example, that want to contribute to this particular program to have the material included for which there are no data sets, and perhaps could be either used as validation test cases or for development of solutions for that particular material set relative to what is already known in the data that already exists in the NextFlex ecosystem. Any high conductivity, so high conductivity, for example, is a sought after goal. I know there is a delta in terms of what's the expected resistivity for additively printed circuits versus some of the subtractive ones, but there are some more recent materials, for example, that have yielded much higher performance, and we would love to include some of those as well. Thank you.
Thank you, Pradeep. I believe our next presenter is in person as well, Matthew Robinson from Terra Circuits. Excellent. All right. Matthew?
Thank you. Good morning. And thank you for Scott and Malcolm for the introduction this morning. It really informed me, and I'm going to actually change this information on the fly as a result of it, and hopefully be able to update the slide in the permanent record. In fact, the first point is maybe the topic is wrong, but at any rate, perhaps the projects for 2 new leads is more appropriate. But nonetheless, the opportunity and the ask is accurately reflected. Terra Circuits' business model is we've developed a material that enables laser-induced forward transfer manufacturing process. We like to call it light-induced forward transfer, because we are able to show that our material works at very low fluences. So where we're at right now is we have an R&D prototype where we can transfer dye en masse to sticky substrates, so dummy dye to sticky substrates, and what we're asking is partners to help us turn that into fully electrically connected devices, so there's 2 opportunities for partnership. So that was one of them. Another one is to learn more about find an academic group perhaps, or maybe an industry group that does that kinetic modeling, so that we can improve the material. For some of the customer bases, would prefer to move from deep UV to more near UV light. And let's see, the type of partners would be equipment partners that we can prove out yield, prove out speed, and low cost of ownership. We want to go from dummy dye to live dye and live devices, perhaps from rigid to flexible, although a lot of our customers, we're in 2 spaces. We're in micro LED space, and we're also in semiconductor companies are interested. And since this is NextFlex, we think we can offer to FHE. That's it. Thank you.
All right. So I believe I don't think we have any slides for 8.5, is that right? So we're going to move to topic 8.6, which is the open topic for new leads. We have 4 slides for this, 4 speakers for this. One in person, Dr. Eugene Chow from Park, if he's here. I don't see Eugene. Oh, sorry, there he is. So Eugene, floor is yours. Oh, I'm sorry, we're out of order. Can we go to Eugene's slide first, please? There we go, thanks.
Yes, I work at Park. We're a research lab near Stanford owned by Xerox. And there's a technology we've been working on which I think can really help this field. We take thin film processing, control the stress very carefully so that we can actually make 3D interconnects. So instead of solder and bonding and all the strong theory of packaging where we make it as strong as we can with this brittle material for the flip chip, you actually use a thin film and a pressure contact, or we can put just the tip in solder. We've done package test vehicles, a few in Asia on the right with the LCD driver. We published a lot with Sun Microsystems to show a CPU-like package from a few years ago. And the key new properties that we can offer this field are reworkable interconnects, compliant, different heights. You can have very large gaps, very small gaps in the same planar layer. Extremely high density. We've done 6 microns. It can go farther. It's lithographic. And integrated test and packaging. When you put more and more chips together, you need 100% yield or you pay through the roof. If you can have a test probe card where you can test many different chips at once, you can use this as a known good module tester. Or if you believe our reliability data, or we can get more reliability data with you, you can actually use this as the final package interconnect also. So we're looking for partners interested in this technology as well as other improvements we can make to it. And so please come up to me anytime today, and I'd love to see if we can work together.
All right. Excellent. So our next speaker is virtual, Madison Maxey from Lumia.
Okay. Okay, great. Hi, everyone. I know there's a lot of text here, so I'll basically just read through everything for what we're thinking of for our proposal. Just as context, our company is called Lumia. We make soft and flexible electronics. So far, we're working with Sunray Scientific that does anisotropic interconnects for this project, and we're proposing doing an FHE heating system benchmarking for cold weather soldier systems. This is in the field of advanced materials for a military critical technology area, and it falls under a wearable technology application as part of the Next Flex timeline, milestones that they're hoping to meet over time. So for our proposal concept, cold weather continues to present a significant adverse impact on military operations, historically accounting for 10% of all casualties in earlier wars. Flexible hybrid electronics can provide lightweight and efficient heating elements to provide cold weather gear, but this approach towards garment heating is not yet well evidenced and researched. Therefore, we propose a benchmarking project comparing and testing FHE heating systems to be implemented in warfighter gear. We suggest comparing traditional wire heaters and carbon fiber heaters with printed ink on polyester, Kapton and TPU, liquid metal solutions, novel magnetically aligned conductive epoxy and other unique materials to create a useful database of performance specifications. The prototype will also incorporate this anisotropic conductive epoxy interconnect technology that is more lightweight than traditional interconnect methods and has demonstrated strong performance at cryogenic temperatures, which will be benchmarked to study improvements in performance, adhesion, robustness, and durability. So in short, it's benchmarking a bunch of different FHE types of heaters against the standard material used in order to build a useful database. So we're seeking a testing lab partner who has equipment necessary for UL 130 evaluation. And we're also seeking technology providers who can create heating samples of some of the materials listed. As background on Lumia, we've developed heating elements for a range of customers from Fortune 500 companies to military clients. It's exposing us to a range of different specifications. We're also well positioned to create a testing plan that is suitable for creating an objective benchmark that highlights key performance parameters related to military-grade FHE heating elements. And as background, as already mentioned, we make a flexible circuit layer called the Lumi electronic layer. The LEL is an award-winning material covered by 6 patents, and our soft flexible circuit technology is designed to integrate easily with textiles for a range of industries. So in short, we're interested in working with anyone who wants to make a heater for a benchmarking study, and we'd love to work with a testing lab partner who can help us to do or execute a testing plan of these materials that we collect. My email address is here on the slide, and thank you very much for your time and for your consideration.
All right, thank you very much. So I believe our next speaker is Jonathan Wells from UT Austin.
Yes, can you all hear me?
Excellent, yes, floor is yours.
Okay, so yeah, I'm presenting on behalf of my professor, Nanshu Liu, and like we said, we're from UT Austin, and currently the wearable technology field that we research in has a big limitation when it comes to powering the devices because most of the power sources are rigid. So a lot of the field has moved towards wireless power transfer to power these devices. However, they're still not stretchable enough to be human compatible and conformable. So we're looking for a better way to power them. So previously, we've worked with a wireless power transfer system with Dr. Nathan Lazarus, who is attending this conference in person. And the project was under the U.S. Army Research Lab and Army Research Office. And we basically built a wireless power transfer system for these type of devices. But one of the things we found out while doing this device creation was that these antennas have limited flexibility and stretchability. And when they are stretched, they tend to degrade the performance of the wireless power transfer system because they change different parameters under the deformation. So we need to find a better antenna. So that's where we get into this Kirigami structure. So we looked at some previous research and saw that basically by introducing microcuts to a material, they can have more stretchability. And this type of stretchability doesn't impact the material performance or parameters as much. However, because of these like microcuts and patternings, it does tend to lower some of these initial parameter values because there's less material. So that's where we get into our actual idea, where we're looking at these Kirigami-inspired liquid metal hinges. And the idea is to basically cause macro cuts to an antenna and then use liquid metal droplets as hinges or joints to join the cut antenna. And this will allow us to potentially increase the cut size, stretchability, flexibility, and the initial electrical conductivity while still maintaining the benefits from the Kirigami structure where the parameters don't change that much under these deformations. So our vision for this project is to basically provide seamless power transfer without disturbing the mechanical reliability or the human comfort. And the collaborators we're interested in looking for is collaborators in the self-assembly research field familiar with Kirigami design. Thank you.
All right, thank you, Jonathan. All right, I believe we have one more speaker who had pre-submitted slides, Ian Winfield from Fabricate Labs.
Yeah, thanks very much for the opportunity to speak with you all. So just a quick background on us, we're Fabricate Labs. We're based here in San Diego, and we're an advanced manufacturing company. We've invented and are commercializing a new metal additive manufacturing or metal 3D printing technology that we call electrochemical additive manufacturing, or we call it ECAM for short. It's a purely metal additive technology, and it's pretty different than other metal additive technologies that are out there on the market. The process doesn't use any powder-based feedstocks. It doesn't use any thermal processes or any lasers. Instead, it's using electrochemical feedstocks. So if you're familiar with electroplating or electrodeposition, those water-based feedstocks with metal salts that are dissolved and then thus contain metal ions, those are the feedstocks that we're using. And so that gives us some pretty interesting opportunities. And in particular, we have room temperature processing, and we have excellent substrate compatibility. So what you'll see here are just a few images of some sort of generic demonstrator features. We can produce high resolution structures in complex geometries with high purity materials, things like copper, nickel, tin, gold, platinum, basically any metal that can be electroplated from a water-based or aqueous electrolyte. We can print those materials with high surface finish and, as I mentioned, good substrate compatibility. And you'll see the bottom left, the top left, and the top right images. These are all on FR4 PCBs. And so one of the things that we believe we can pursue is printing onto flexible circuits, various structures in copper or other metals. And in particular, in this case, we're interested in some thermal management devices or heat sinks. We have demonstrated already some capabilities to print on the flexible substrates. So in this case, a potential partner for us would be somebody that is more focused on the actual component or system design and test capabilities. So sort of in summary, the way we think about this is we are a manufacturing company. We bring manufacturing expertise and new manufacturing capabilities. In this case, we're looking for a design and test type of partner. Thank you.
All right, thank you very much, Ian. All right, so now that's the last of the presenters who had submitted slides before today, but on our sign-up sheet that we had outside the door, as people were arriving, we have, I believe, 6 more who have indicated that they'd like to present today as part of the teaming event. So I'm going to introduce speakers in order from top to bottom on this. My understanding is that these speakers don't have slides, that they're just planning to talk to us, which I think is excellent. We'll get introduction. Hopefully we can share contact information as well after the fact. The first one, Volkan Efe from Nano Dimension. Oh, no problem. So I know there's a little bit of, that's right. And you're speaking later on as well for the other event. Okay, so a little bit of uncertainty here. So Vincent Malave from Momentive, were you interested to talk at this point for the teaming event? Okay, so another that has a presentation as part of the member event later today. All right. Marcus Lenz. Excellent. Would you mind coming up to use the microphone? Because that way the online audience will be able to hear you as well. And why don't you introduce your company as well?
Sure. Good morning. I'm Marcus Lentz with Buehler-Leibold Optics. Leibold Optics has been in business for many years in terms, at least on the optics side and semiconductor processing side of thin film deposition with sputter and evaporative I-beam systems. But we also have a part of the business which is roll-to-roll thin film deposition equipment. So I think it's probably, I'm not sure how applicable it is from at least the project call that we're currently, but would be interested in talking and discussing with people probably more on the substrate side of possibly looking at new films, new technologies to deposit thin films on flexible substrates. Thank you.
Thank you very much. All right, the next name on my list is somebody else who has a presentation during the member event later today. Eric Versluis from Fortify. Excellent. Fantastic.
Good morning. My name is Eric Versluis from Fortify. I do have a presentation I'm going to give during the capability discussion this afternoon, but Just real quick, after seeing some of these topics come up, I just wanted to throw out the idea of anybody who's looking for very, very low loss 3D printable substrates. We're looking to team up with anybody who's looking to do, hybrid metallization, lensing, low K substrates through their circuits. So whether in polymer or ceramics, we have some options to do some of that. So I'll get into a little bit more details in the afternoon session on some of our technology and things that we're doing in some of the specific applications. But as you're looking at that and as you're thinking through some of these topics, if there's anybody who's interested in reaching out to me, I'll be here today, and then you can reach out as well online and we can discuss possibly partnering up. So thank you.
Thank you. All right, the next name on our list here, Genevieve Struck from UMass Lowell. No? Okay. In that case, the last is Doug Sharp from Komori. Oh, there you go. Hopefully, this is.
All right, good morning, everybody. Sorry if I stumble a little bit. This is going to be a little bit off the cuff, but my name is Doug Shard. I work with Komori America Corporation. We represent a full line of screen printing and gravure offset printing. The main feature, I would say, of the gravure offset is very fine line definition and printing. We're down to 5 microns. We clean lines, sharp bumps. But one of the things we're working on currently is building bumps on chips, actually, by repeat processing through the machine. It's accurate enough that we can lay drops of conductive material, whether it's ink or solder, right on top of each other and build up the actual bumps so we can get into the flexible chips. Really, we'd be interested in talking to anybody who thinks we might be able to help, because we do testing in our factory, and we would be interested in talking to you. So look me up after the meeting if you can. Thanks.
Thanks, Doug. All right. So at this point, I'll ask: is anybody else in the room want to get up and speak? Andy? All right. Well, we have plenty of time. All right. Andy Quass from Northrop Grumman.
Yeah, sorry, I missed the memo on the way in about the sign-in sheet, so I'm going to wing it. I've been involved with NextFlex since the start, I guess, 2015. And some of the projects we've worked on and the technologies we've learned here has been really influential in a lot of the products we've developed at Northrop. In particular, I've been pushing since the start that we need more space-related things. I'm all for the terrestrial things, but and we certainly have B-21s and things like that we do apply FAG to. But when I see projects like 8.3 and 8.5 and the harsh environments, I think we're looking for a little help there. We have things on the lunar surface like the Lunar Terrain Vehicle going, nuclear power plant on the lunar surface, a lot of planetary and asteroid-related missions, and certainly spacecraft in general that requires this kind of technology. I have to deal with 300-degree temperature swings in a matter of 5 minutes, depending if I'm in or out of eclipse. So my environments are pretty harsh, right? I have to deal with nuclear environments that are pretty bad, just getting through the Van Allen belt to get out there. So I have a lot of things that a lot of this technology can use. And in fact, we have a lunar mission going up. It's scheduled for 2024. I'll put money on it that's going to go leak into 2025 with SI2 on taking some antennas and some 3D printed materials up for both visual inspection and radiation evaluations on the lunar surface on an intuitive machine launch for that mission. So constantly looking for ways. We have a lot of work going on in the company in this area. Cost share is never a problem. In fact, it's embarrassing when you want a 500K and I say, is 50 million enough? Cost share, and it usually is. So anybody have some really good ideas to be able to support that? Like I say, we're already tied in with SI2, but always looking for new partners to be able to show and advance the technology, even beyond what Northrop can use. So Tier 1 primes, Boeing, Lockheed. And by the way, I don't know if it's been announced, but about 2 months ago, Northrop took over the #1 space company in the world. I won't say from who, but we're all friends here, and we're pretty excited about that. So anybody wants to jump on board and help us do some of these projects, I'm actively looking for help. Thanks.
All right. Anyone else interested in standing up and saying a few words about interest? Right? Absolutely. Yep, please. Yep, you. I'm sorry. We've got two hands near each other.
Thank you. Good morning, everyone. My name is Tom Weller. I'm from Oregon State University. We may be one of the newest members of NextFlex. I actually am here representing a group of faculty who work in a variety of areas from passive and active thermal management to millimeter wave CMOS. We have Matt Johnston in the back of the room who's doing stretchable electronics and also on-chip photo electro-optronics. And finally, magnetic materials and magnetic characterization. So like I said, we have a group of faculty who are very interested in partnering, so I'd be happy to talk with anyone who's interested maybe in custom photonic or millimeter wave IC design. Thank you.
All right, Jack, is your hand in there? All right, excellent.
Good morning, everyone. My name is Jack Lee. I am a program manager at UES, soon to be Eclipse. For those who haven't heard, we recently just merged with another company. But here I'm just to share with you that we have a liquid metal ink product that many of you guys are aware of, and we just started releasing out a new screen printing ink. This material, we would like to brag that it performs really well under high strain. And we understand that there's a lot of interested parties of trying to push the limits of this ink that we have yet to explore, especially when we think about like the temperature and how far we can actually push it. And I'm looking at a professor here from Auburn regarding that area. We haven't seen the limits of that, in which actually our limitation is mainly due to the substrate failing before we can actually see how far we can push the ink. But the conductive ink itself, again, is commercially available, and I'll be here this afternoon with some prototypes in which we developed for wearable heaters regarding to DoD applications later this afternoon. So I look forward to discussion with many of you and meeting you all. Thank you.
All right. Do I see any other hands in the air? All right. I think that's the last of our presenters. Oh, sorry, one more.
So I'm John Williams from Boeing. I'll just stand up and say that we're looking at probably every single one of these projects for different teams and different collaboration organizations. Feel free to reach out. I'm here for the next 2 days, and all I plan on doing is meeting with people to discuss the possibilities of what we can do together. Thanks.
All right. Last call. Oh, sorry, I've got a column in the way. Thank you.
Hello, everyone. My name is Mayank Gupta. I'm from Applied Nanotech based in Austin. So we make conductive inks like copper, silver, and different metals. And so we have an ongoing project, and I saw that there are calls for like harsh environment electronics. So we have indium. We have been developing indium inks and paste. So we are looking for partners, and I mean, we are new members. We don't know how to work for these project calls. So we are interested if you're looking for some ink or developing an ink or paste. Thank you.
All right. Thank you very much. Sure. Yeah, absolutely. This is great. The whole point of the event is for people to identify. The partnering event is for people to identify themselves and their interests, and make some connections that they can leverage, going forward. So, and we'll keep going.
Okay,
absolutely.
No,
No problem.
the last chance. Hi, everyone. I'm Rory Grondin with LPKF Laser and Electronics. Oh, sorry about that. Rory Grondin again with LPKF Laser and Electronics. this is my first event here. We are non-member, but I think a lot of you are familiar with our laser systems and what they can do for subtractive processing. And I think it can actually benefit a lot of the additive manufacturing. There's opportunities where laser structuring, I think, could actually help roughen the surface of some of the materials before additive printing, remove some of the adhesive material itself when you do bonding. Multi-layer flex is kind of the newer development, and we have a new lamination press that can actually get up to 320 degrees Celsius, bond flex to flex together without pre-preg, has a vacuum chamber and so on that take out air bubbles during the development process. But we have equipment, and LPKF actually offers to do like a one-off sample if needed to help prove concept, or I can help network and connect anybody with somebody in the membership through NextFlex that has our machines and might be open to doing some services. I don't believe UCLA is a member. I'm not aware, but definitely helping to help connect where I can. So feel free to ask me any questions, and I appreciate it. Thank you.
I'll take one more look around the room. I'm great. How are you? Absolutely.
So at first I thought many of you guys know who we are, but there's so many new attendees, so I wanted to introduce ourselves. I'm Madhu Stemmerman, CEO of Sunray Scientific. Some of you may have heard about what we have. We have a magnetically aligned anisotropic conductive epoxy. We've done a lot of work with many of you in the room, a variety of reliability testing that's been done on our technology. NextFlex, you guys have our kit. So we do offer a kit now with our magnets as well as our materials so that you guys can work with our technology. But bottom line, we've done a lot of work on attaching LEDs to flexible substrates, various components to flexible substrates, and showing phenomenal adhesion, very good manual bend test, very good shear strength. We have some work to do. So I know Boeing, and Pradeep, we're doing some work on QFNs and BGAs. So for complex connections, we're still doing some work and would love to partner with you guys to continuously demonstrate our capabilities across various applications. A couple of other things, we've done some work in the RF arena. We're showing greater than 90 gigahertz, and we want to take that even higher. We've done pad pitch down to 100 micron pad pitch, and we want to take that down to less than 50 micron pad pitch. So come talk to me. Would love to work with you guys. Again, we've demonstrated some really good capabilities and continuously demonstrating further capabilities across applications. Thank you.
All right. Last call. All right, in that case, a couple of announcements and then we're going to go to break. So first, we haven't mentioned before, there is an opportunity to partner with NextFlex on projects. If you're interested in doing that, obviously, as with any other partnership, the sooner the better. You can contact us through the proposal at nextflex.us address, or you can contact Art Wall, Janusz Verish, myself, Nick Morris, and we'll put you in touch with the right people for that. The last is that there was a question that's been asked about slides being made available. Yes, slides from this morning will all be posted on the PC8 website, as will the recording of the event. So you'll have access to all of that as soon as we can make them available. All right, we now have a 30-minute break scheduled in the agenda, and we'll come back from that, and we'll have our MRL briefing from Dr. Mark Gordon. So thank you very much.